Last time we spoke about the complex exponential and its behavior, and how it represents a point on the unit circle going counterclockwise if omega is greater than 0, and clockwise if omega is negative. And how do you feel about that behavior? Associated with the time-dependent complex exponential are, of course, the sine and the cosine. So we usually classify the complex exponential, its corresponding cosine, and its corresponding sine broadly as sinusoids. And they belong to a class of signals called periodic signals. And by periodic, what I mean is that, let's say, a signal, so here's a definition. A signal or a function x is periodic if x of t shifted by some amount p is equal to x of t for some p greater than 0 and for all t. You take a signal, you shift it by p. If you get the same signal back, that signal is periodic. A prototypical example, of course, is the sine or the cosine. So here's the time axis. Let's say this is 0, so I'm plotting the cosine. The distance between adjacent peaks is what? Huh? P. That's what I mean by this P. So the P is called the period. It corresponds to a frequency omega naught, which is 2 pi over P, and that's called the fundamental frequency. So in this case, you know that if you take this cosine and shift it by p, actually I shouldn't specify this is greater than 0 yet. I just specified that it's not equal to 0. So you take the signal, you shift it by p, either to the right or to the left, and you get the same signal back. Okay? The smallest positive P is called the fundamental period. And 2 pi over that is called the fundamental frequency. So you could potentially have two signals that look different but have the same period. So for example, I can have a square wave. I can have a square wave that does, oops. That behaves like that. Okay? And the distance between the starting edge of two peaks is the same p as above. And this signal, too, will have fundamental period p. And fundamental frequency 2 pi over p. And periodic signals are very important because we can decompose a broader class of signals in terms of periodic signals. And so if we know how a system behaves when you feed it a periodic signal, you can figure out how the system or broad class of systems behave when you feed them more general signals. Now, those of you especially who are into music have seen these before. So let's try to do the demo that I attempted last time when my computer crashed. Okay, on laptop, and this is on. There we go. Oh boy. Here we go. Okay. So I'll start with the phasors, which I've already shown you. These are essentially the complex exponentials that you've been looking at, or we've been looking at. Apply values. And it would help if I turn off the lights. Why is it not applying the values? Okay. 1.25. Yeah. Oh, there we go. Do it. Amplitude is 0? No. Two. All right, let's uncheck that. Here we go. Okay. So this is a phasor. It's rotating at frequency 1/4 of a hertz. And as you can see, because 1/4 of a hertz is a positive number, it's rotating counterclockwise. Its projection onto the real axis, which is the horizontal axis, is what? Cosine of 2 pi. 2 pi what? And what's omega? No. It's not 2 pi omega. It's 2 pi f. My chalk is... omega equals 2 pi f. F here is 1/4 of a hertz. So omega is 2 pi over 4 pi over 2 radians per second. Okay? So the projection onto the real axis is cosine pi over 2. Pi over 2 what? T. That's what you see on the horizontal axis. That's what this cosine waveform is. Now, you remember we had the formula cosine omega t is e to the I omega t plus e to the minus I omega t over 2. Okay? So right now, if you actually look at the tip of the yellow vector, the phasor that's rotating around the unit circle, it's not a real valued function. It's a complex valued function. The reason we see this waveform in the bottom is that we're only projecting it. We're ignoring its imaginary part. If we want to create the cosine out of phasors, we really need a second one at what frequency? Negative 0.25. And if I click that, now you see you've got, why is the amplitudes are, there we go. So now you see that the two phasors, the blue ones, each of them is rotating, the positive frequency one is rotating counterclockwise. With a vector addition, we're adding the other phasor at negative 1/4 hertz, and that's rotating clockwise. If you notice, this second one is rotating clockwise at the same frequency, except the negative of that frequency. And that's why the tip, the vector sum of the two, is always on the real axis. And that's what you want. So that's exactly the cosine. Cosine is a real valued function. Okay? So I encourage you actually to go on the Ptolemy website and play around with these Java applets, just to get a feel for how these complex exponentials behave. Now let's go to musical. Scale. Here we go. So if you want to create a famous note in music, the major triad, you can create it using 3 different sine waves. And somebody who's into music, tell us which ones I should. A. Yeah. Let's. C sharp and E. It's a happy, jolly note. And the minor triad is what? A, C, A, C, and that's a sad one. Okay. Now let's go to the major triad. Let's be happy. Now here you see all the 3 waveforms. So I think we can do away with the sound now. Here's A. It's a sine wave at 440 hertz. So A you can represent as 2 pi times 440 times T. Plus C sharp is at 554 hertz. 5 what? 554, right? Who's talking? Yeah, it's times. This is a dot. Plus sine. So this is A. This is C sharp. And this is, and the last one, E, is at 659 hertz. It's the sum of these three waveforms that creates the major triad. Okay? So you see a lot of this kind of frequency decomposition in music. Now so here, what you see is the sine wave for the A note. Here's C sharp. It's a higher frequency, so it oscillates faster. And here's E. Okay? Now, if I put all of them together, they're all color-coded. Now, I'm going to unclick this Show Components button, and that's the overall signal after you add these three sine waves. And that's what sounds like the major triad. You can play around with these and have some fun while you learn things about sine waves. I also want to show you, let's see, where was it? Something about phase. Oh, here we go. So let's say I plot the A note. Okay. Oops. A note. This slider down here allows you to change the phase, or allows you to time shift the waveform. So I move it, and you can see it moves. And now let's add C sharp and E. And this Java applet unfortunately doesn't have, actually it doesn't need to have sliders for the other notes. All you need is a slider that allows you to change the phase of one of those sinusoids, namely the A note, relative to the others. I'm going to unclick the components. So this is the major triad. I'm going to now change the phase of the A note. And I'm going to play the sound and notice what happens. Notice what happens to the shape of the waveform, the overall waveform, and tell me if you hear a difference. Ignore that beating sound because that's probably from my computer. But can you tell the difference as I change, as I slide the phase? Yeah. That's because the human ear is quite insensitive to phase differences. That's in contrast to the human eye, which is very sensitive to phase differences. And if you continue on this track and take more advanced courses in signal processing and end up taking courses in image processing and video, this is one of the things they'll talk about, and that's one of the things they exploit. There are, in fact, algorithms, image reconstruction algorithms, that can reconstruct an image to quite an intelligible degree using only the phase information about the image. And you'll learn a lot more about the phase component and the magnitude component as we go through the class. But with respect to the human ear, shifting one of the sinusoids relative to the others didn't make any discernible difference as far as you could tell. Of course, there are limits to all of these. I mean, if you can have two sinusoids that, when shifted relative to each other, can destructively interfere, and you'll lose your signal, or you lose a substantial part of the signal. So we're ignoring those. But within quite a robust range, the human ear is insensitive to phase differences. And that's one of the things that you discover when you play around with some of these Java applets. I think that's about, let me see. Yeah, that I did. That's about it. So, let's see, where are we? What's that? Bonsai. Okay, fine. Hey?
Could you speak a little more about phase difference of sight? Like, why does it work differently for your eye?
It's just okay, folks. Yeah. Shh. Phase information. But the thing is that you're still not equipped to know what I mean by phase information. In one dimension, for these particular signals, it's easy to understand. So I take a sine wave, and I add an angle to it. That's the phase. And we'll do some plotting later in this lecture. No, you can't map it to a time domain behavior, or in the case of images, in the spatial behavior in a straightforward manner. Because there's a transform that takes you from the space domain to the frequency domain. In frequency, you have a complex valued function. And that complex valued function will have a magnitude, and it will have a phase. Well, when we say that we can reconstruct an image from that phase information, that means we can toss out the magnitude and look at that phase. What the relationship is between that phase and to the space, it's not something you can eyeball or say this is the relationship, because it's a mathematical mapping. Okay, so actually let's do this, since it's come up a few times already. Suppose we're looking at a sine wave or a cosine wave, and we want to see. So what I did in the slider in the demo was to look at a sine wave. So here's an x of t. It's got a particular frequency. And now I add an angle. So this is the frequency. and this is the face. Okay? I plot it. I plot the case where phi 0 equals 0. In other words, I'm plotting sine omega naught t. Go something like that. This is 0. And what would this number be? This number. It's p, but what is it? 2 pi over? Over omega naught. Okay? And this is my vertical axis. So this is x of t equals sine omega naught t. Now suppose I introduce a non-zero phase shift. And say phi naught is greater than 0. Okay? Which way does this sine wave move? Left or right? Left. So here's the 0. Now my sine wave is going to be like this. And there's a shift to the left. I call that T naught. I want you to find, actually, let's do the case where phi naught is less than 0 also. So this is 0. This is 0. Now what do you think happens? Shifts to the right. So the 0 crossing is now to the right of, the first 0 crossing is to the right of 0, and call that T naught. I want you to figure out, talk to your neighbors, and determine T naught in terms of the known knowns. Omega naught and phi naught. Okay? I'll give you 3 minutes. That's a very generous amount of time. You don't really need 3 minutes. Meatball. You're on.
Alright, so I'm thinking
Okie dokie. So we have x of t, which is sine omega naught t plus phi naught. And you're trying to find the location where it first hits 0. So you want x of t naught, x of t naught to be 0. And the smallest t naught that does the job is the answer we're looking for. Subject to our knowledge that if phi naught is greater than 0, we're shifting to the left, and if phi naught is less than 0, we're shifting to the right. So that means, so you've skipped you've skipped a step. Tell me how you get that argument to be 0.
Well,
Sine 0. So the argument, so we want sine omega naught t naught plus phi naught. We're after this t naught. We want the sine to be 0, which means the argument has to be 0. And so t naught is what? Negative t naught over omega naught. Okay? Is that clear? Another way you can look at this is to ask yourself a question, alternatively. Ask yourself the question, by how much do I need to shift x to get sine omega naught t plus phi naught? How much do you need to shift the signal x to get, that's not what the shifted version is. What is the shifted version? If I shift it, wherever I see a t, I have to replace it with a t minus t naught. Like that. And so I'm left with sine omega naught t minus omega naught t naught plus phi naught. Did I get this right? I always mix the signs. Let's see. This is my original signal. This is my original signal. By how much do I shift to get I want this, so x of t minus t naught, which is sine omega naught t minus omega naught t naught plus phi naught. I want this to be equal to the sine of omega naught t plus phi naught. How much do I shift the original signal? No. Yeah. Let's backtrack. Sorry. I'm still booting today. If x of t is sine omega naught t, that's my original signal, how much do I shift this? So ignore this sentence here. How much do I shift this sine wave that crosses 0 here so that I get, so what is that? What is the shifted version? Sine of omega naught t minus t naught. And by shifting that, I want to get sine of omega naught t, so we want omega naught t plus yeah, this is correct. Plus phi naught, the shifted version, the one with the phase. So you have sine omega naught t minus omega naught t naught is equal to sine omega naught t plus phi naught. So what must hold? Negative omega naught t naught must equal phi naught. And that's the same. So you get the same expression for t naught. Okay? So when you introduce a phase phi naught, phase shift, you can find it by looking at the unshifted signal and say, okay, by how much can I shift it to get this signal? And then the rest is algebra. But Meatball's method is most appropriate for this particular example. Because with sines, you know where the zero crossings are and so on. So he looked at the first zero crossing. So, okay. My first zero crossing, I want it to be at t naught. The argument has to be 0, and you solve for t naught. Now, there's a lot we can say about these sinusoids. One phenomenon that you may have studied in physics is the beat phenomenon. Suppose I have a signal x of t, which is cosine of 2 pi, let's see, 102, 2 pi times 2t plus cosine of 2 pi times 100 t. Okay? There are two cosines. Notice the frequencies are substantially different from each other. So this is 2 hertz, 2 hertz, and this is 100 hertz sinusoid. We want to somehow plot the result. So what I'm going to do is give you one of those obscure trigonometric relationships and have you work through the rest of it. So that relationship is trig identity. Cosine alpha plus cosine beta is 2 cosine alpha plus beta over 2 times cosine alpha minus beta over 2. Okay? Now I want you to use this useful trig identity and rewrite this summation or this superposition of two cosines as a product. And then I want you to plot it. And discover why we have this quote-unquote beating effect. Is everybody clear what we want? So use the identity. change this sum of two cosines into a product of two cosines, and then plot. I'm not talking. Stop. Today is really my day. I goofed on the numbers. I can't believe I did that. Where is my chalk? my other show. Ah. Forgive me, please. I just realized that they use this property. In the old days, they used to use this property that I'm trying to illustrate to tune musical instruments. So they would have a tuning, the musician would have a tuning fork, and he would strike the tuning fork, and then at the same time play the instrument. And then depending on the length between the two beating effects, if the length of time between two beating effects was large, he would know that the instrument is tuned to the frequency that he wanted. And that's how I realized there's a bug in this problem. So what we need in this one is to change that to 98 and change that to we can keep it 99 and 101. So it's when you add, remember earlier I said when you have two sinusoids, they can start destructively interfering with each other. So these are two sinusoids that are fairly close in frequency. Okay, the difference between them is negligible compared to their size. So this is frequency around 100 hertz. This is around 100 hertz. But the difference between them is 2 hertz, which is much smaller than 100 hertz. So they're very close to each other in frequency. So you can think of one as the instrument, the other one as the tuning fork, and you're now trying to tune. And you look at the closer these two are to each other, the longer the beats. That's what we're trying to find, okay, through this exercise. So sorry about that. Let's do this again. So you have 101 hertz here, and you've got a 99 hertz here. How are we doing with respect to the answer? Should I sick meatball on you? How much more time do you need? He's going to break through that chain, meatball, here. I'll give you another minute. But only if you're talking to each other. If you're not talking to each other, that means you're done. Okay. Meatball, pick somebody. Oh, you got to just point to somebody. They can't count. I think you're out of the chart. Just see who's making, just pick somebody. There's a lot of psychology. You notice that when you try to pick somebody, people don't look at you. They don't make eye contact. And you are? Tyler. Go for it, Tyler. So x of t using the identity is? Yeah, break it up for us. Times what? 50? So you got to add. So here we have cosine omega 1t plus cosine omega 2t. And according to the identity, this should be cosine, 2 cosine omega 1 plus omega 2 over 2t times cosine omega 1 minus omega 2 over 2t, right? So tell me what these are for our particular choice of numbers. 2 cosine. Omega 1 plus omega 2 divided by 2. You've got the 2 pi. So what do you have to add? 101 and? Which two numbers do you have to add and then divide by 2? Huh? 101 and 99 divided by 2t times cosine. Now? It doesn't matter because it's a cosine. 101 minus 99 divided by 2t. So what is the first factor? That's what? 100 t times cosine 2 pi times t. So this is a cosine at 100 hertz. This is at 1 hertz. And so you're essentially, forget about this 2. This 2 doesn't really matter. To get the shape right, what you care about is that you're multiplying a cosine of a high frequency with a cosine of a low frequency. And how do we plot it? Calculator. Nice try. Okay. You are? Jeremy. So you plot the 1 hertz signal. And its reflection. So this is the cosine 2 pi t. Okay? The reason I've stretched it out like this is that this is pointwise multiplying a much faster oscillating cosine. So the other oscillating cosine goes like this. And at each instant in time, the amplitude of the other cosine, the faster cosine, is, and the term is modulated by the slower cosine. And then there's a 2 here, and minus 2. this in a block diagram form, you have a signal f of t being multiplied by a cosine, let's call it omega 2t here, which is usually much faster varying than the signal f of t, and you get some signal. Okay. Amplitude modulation, your AM radio, works based on this kind of an operation. At its core, this is what happens. So this is the voice signal. Whatever, let's say I'm on air, and I'm speaking into the microphone. And the system takes my voice, multiplies it by a very high frequency signal. That maps the frequency content to a part of the frequency spectrum that's much higher and can travel long distances across the atmosphere. And we'll talk a lot about that in this class. That's the signal that gets transmitted. And at the other end, they do the reverse of this. So in this case, one of the two signals is f of t. The other one is this cosine. The slower varying one will be here. The faster varying one will be here according to our diagram. And that's the product. So if I have an arbitrary signal, let's say this is my f of t, and I'm multiplying it by this very fast varying cosine, what kind of a shape am I going to get? According to what Jeremy just explained. I've deliberately drawn the signal to be non-negative. So I draw the mirror image of this. And then what? And then the fast oscillatory behavior. It's this signal. It's supposed to be purple, but it's not showing up properly. It's this signal that gets transmitted. This is called amplitude modulation. And that's where the term AM comes from. So in the example with the superposition of two cosines, the two cosines were very close to each other in frequency, and they were superimposed. And using the trigonometric identity, we wrote it in terms of a modulation expression, the product of two signals. And you notice the slower varying cosine acts as an envelope, just like this slowly varying function f acts as an envelope, for the faster varying cosine. And where the fast varying cosine after modulation reaches 0 in amplitude, those are the beats. So each of these blobs will act as a beat. Yeah.
I'm kind of curious. So if you multiply by a higher frequency, will you be able to preserve the original better, or is it not?
This one? In this example?
That, like, if you use a much higher frequency, will you preserve the original better?
Very good question. So what happens when I modulate my voice with a much higher frequency than omega 2? Okay, does it make a difference? Well, it depends on how far you want to send the signal. In general, in the old days, actually, there's still broadcasts in the shortwave where the frequencies are much higher. Now we're even into microwave, so the frequencies are much higher. It depends on how far you want it to travel. If you don't want it to travel much, then you can stay at lower frequencies. The point is that the atmosphere acts like a filter for the signals. It attenuates lower frequency signals much more than it does higher frequency signals. So my voice At most, it's going to go to what? 15 kilohertz? At most. I mean, if we stretch the limits. No matter how loudly I yell, my voice is going to carry only so far in the atmosphere. So in order for my voice to be transmitted to, let's say, New York, I'm going to have to do a serious change in the frequency of my voice. So this will act as a carrier for my voice. It produces a signal that if my voice, for example, if this is the real estate on the frequency axis, just like the time axis, we can plot these. If my voice occupies this region, so this is my voice. It occupies this amount of real estate on the frequency axis. Then what this guy does is it shifts. This is called the spectrum of my voice. Then after the amplitude modulation, preserving the shape, it creates that, if I multiply it by cosine, it creates two replicas, one centered at omega 2 and one centered at minus omega 2. And the way this is produced is something we'll go over in this class. This is very elementary. You won't even need, all you need is knowledge of high school trigonometry to figure out why this happens. But we'll explain it with much greater depth in this class. I'll talk about amplitude modulation. So zero frequency, which is where my voice used to be, is now empty. And the spectrum of my voice, a replica has been transmitted here, has been shifted here, and another one here. And this is what YF, this is the spectrum of Y. Spectrum of Y. And we call it with a capital letter, and it's a function of omega. Whereas the other one is f of omega. Okay? But we haven't explained what this is. This is just a graphical representation of what you can expect later on. Yeah?
How does one retrieve the original frequency after it's been transmitted?
By a process exactly the same. You multiply it by another cosine. We'll see. We'll go over it. You multiply it by exactly the same cosine. And it'll shift one. See, what did this do? What did the first stage do? It took my spectrum, which was here. It shifted it to the right, and it shifted it to the left. It also attenuates by some amplitude, but that doesn't matter. It shifted it to the right, and it shifted it to the left. Right? Correct? So now at the receiver, this is what you receive. Multiplied by another cosine. It takes this pair, shifts it to the right, so this guy gets shifted to the origin. And it also takes this pair and shifts it to the left. So this guy comes to the origin, and you get the original spectrum, but you have two extraneous ones, which you can filter out.
Does the one at the center get a higher amplitude now?
No, because these are half. These are, see, I told you your education is a process of diminishing lies or successive refinement. Sorry, this is 1. If this peak is 1, when I multiply by a cosine, you get a half of that spectrum and a half. Now the receiver is going to multiply it by a cosine again. So you take this and shift it to the right. So you get this 1/2 showing up here. It also takes this and shifts it to the left. Whatever it takes, it shifts it to the right and to the left. So this guy now gets transferred here, and the superposition of these two will give you the original. Then you take a filter and get rid of the higher frequency portions, and you get your voice back. Pretty spiffy. So let's go back to this beat. If you have two signals, let me not, I think I'll have enough space here. So here we had a signal x of t, which was a cosine of omega, what did we call it? Omega 1t, plus cosine of, let's say, a frequency that's only slightly different from itself. And I call that epsilon. That small difference is epsilon. When you use the trigonometric identity, you notice that this is equal to 2 cosine of what? Omega 1. No, not cosine squared. Cosine of the first frequency plus the second divided by 2. So what is that? 2 omega 1 plus epsilon divided by 2. So it's omega 1 plus epsilon over 2 times t times cosine of the first one minus the second one divided by 2. It's epsilon over 2, epsilon over 2 t. Are we all here? So I'm adding two cosines that are very close to each other in frequency. One of them is at omega 1. The other one is just ever so slightly different. According to my identity, this is equal to the product of two cosines, where the first cosine is has the frequency which is the average of the other of the two frequencies, and the second one is the difference divided by 2. So notice, the closer they are, in other words, the smaller the epsilon, the slower varying this second cosine, which means the longer this envelope gets stretched. Correct? Cosine of a very small frequency. This is a small frequency, so its period is large. Period is always the inverse of the frequency. So the period is large, which means the distance between the beats is large. And that's the principle that in the old days, when people wanted to tune their instruments, used. If the time distance between when you hear the beats or when you suddenly hear the sound go away is large, it means your instrument is pretty close to the reference, which is the tuning fork. Got it? Now go away.